You everyone for coming. Start again. Thank you everyone for coming. Today we have Anthony Ciavarella, who is from the physics division here at LBL. He's a postdoc, been here about a year, graduated from University of Washington, which I will say parenthetically has a great physics program. And he's going to talk to us about the simulation of lattice gauge theories.
Thank you. Yes, today I'm going to talk about how to use some simulation to explore features of particle physics. We try to explain all the entire observable universe in terms of fundamental particles. Right now, in the standard model, we describe things in terms of quarks, leptons, and gauge bosons that mediate forces between them. So, to weaken electric forces, we're able to describe using perturbation theory in most situations we're interested in. On the other hand, the strong force is not perturbed. Make predictions with it, we usually have to resort to linear. So the way we do that is using formalism we call Lattice QCD. So Lattice QCD, we take the quarks in our first break space-time up into several discrete points, and we place points for a lattice, and then we place our gluon fields on the links between them, and then we can construct operators that help with those. That's this every psi term describes how the quarks are called gluons, and this ket operator that forms the product of gluon operators going around one square, which describes how the gluons interact with each other. So, to use classical computers, we can Monte Carlo simulations for the static properties of the theory. So this program has been immensely successful in computing things like hadron masses, form factors, and some elastic Sagan. Also, the contributions to T-2 particles. However, classical computers, there are some things we can't compute, just the presence of the sign problem. These include things like real-time dynamics and finite density systems, which is somewhat unfortunate because these are things that exist in the real world, and we'd like to make real predictions for either relevant to things like physics of the early universe or situations inside a neutron star. And so to simulate these scenarios, we are going to try to use quantum computers instead. And so the reason why we think quantum computing might help goes back to ideas first written down by Feynman in the early 1980s. This paper on simulating physics with computers. So in this paper, he was just trying to formulate what counts as an efficient computer simulation. So generally, you want the size of your computer to scale linearly with the size of the space you're simulating. The time that the calculation takes should be proportional to the amount of, directly proportional to the amount of time you spend simulating, running the simulation, and then your computer should only have local connectivity between your components because if building a computer, you have to connect things together. And so this creates a little bit of a problem when you try applying it to simulating a quantum mechanical system, a possible one, because this is essentially taking a quantum system and trying to simulate it with classical variables, which, you know, from Bell's theorem, there's certain states that you can't represent this way. So according to Bell's theorem, we would expect that simulations of systems that are at large entanglement never be done efficiently classically. So the alternative that proposed was to instead engineer a quantum system to simulate theories we wish to study. So we expect that this will help us solve some of the problems that we can't currently do in speed. So generally, the way we were going to set up a simulation, gauge theory, first we need to pick our lattice regularization, our Hamiltonian. So this includes how we're mapping the theory onto on computer and what Hamiltonian we're working with. We prepare this development state. Since most quantum computers start off in the state where all the qubits are zeroed out, but often that's not the state we're interested in studying. So we're going to have to do some work setting up more physical or interesting initial state for our calculation. And we're interested in doing dynamics. We need to perform real-time evolution. Trying to start to do that. And all quantum computers have some degree of error in them, so we find ways to mitigate errors or they just correct them in the middle of the calculation. And then also we need to figure out what rules exactly are we going to measure at the end of our calculation to extract the physics that we want to study. For example, if you're studying scattering, what is the simulation version of the detector that tells you where your particles are on the lattice? And so there's been some work studying small quantum, simulation of small quantum systems. For example, this work from 2020, where we got just a single square on a lattice and with that an SU3 gauge field involved on it. We're only able to do up to 4 tri-steps before the noise. But using some improved error mitigation techniques, we're able to go back and push this calculation to much longer amounts of time, which corresponds to a much deeper circuit. And I'll talk a bit more about error mitigation use in this calculation later. And so in the last year, there's been a push towards doing more large-scale quantum simulations. So this figure, the x-axis is just circuit depth, and the y-axis is the number of qubits. So about a year ago, IBM put out this figure talking about where they expect quantum utility to occur. And so these red points are the simulations that were included in that figure. And so they figured quantum utility would start to occur once we begin to do calculations in this regime. And so over the past year, we worked on a few papers, projects that put us into this regime of potential utility. So this way all the way out here, where we have a circuit depth of around 370, is going to be one of the things that I'm going to discuss today. But before I get to that, I need to talk about the Hamiltonian that we'll be using to do the simulation. So the Hamiltonian formalism for the last gauge theory was first worked out by Kogan and Susskind back in the mid-70s. So start with what gauge field degrees of freedom look like. So on each link, we have an Hilbert space, which can represent magnetic basis, which is just continuous Hilbert space with elements given by elements of the gauge group. So it's not ideal for quantum simulation because qubits have discrete degrees of freedom, but our gauge group is continuous. Alternative is to use what's called the electric basis, where instead you're working with irreducible representations of gauge group. So if you're working with SU2, your basis will look like having a palm rotor on both ends of each link. If you want to do SU3, it would be conceptually the same thing, just with representations of SU3 instead of SU2. And this electric basis, your U operators for the diagonal magnetic basis act on rotors by just changing the value of the angular momentum that's present. And you can write down your here, which first term is just the electric energy, which electric basis is diagonal. And then you have your sum of cat terms, which earlier is just the product used one around each square of the lattice. Sum of variables instead. And so because the electric basis is discrete, you can map it very easily onto qubits. And there's a number of different approaches people have thought about on how to do this. I'm not going to go into detail into any of them today. Still an open question on as what is the best way to do this coding. So that's how we get our gauge fields onto all aspects to do QCD. We also have to include the quarks, which are fermions. And so we can do that by just by taking our quark component fermions, just putting a single node on each side of the lattice. So this formalism is referred to as staggered fermions. These are sort of splitting the spin nodes onto different sites. And the reason you do this is to ensure that you get the right number of quark flavors back continuum. So if you use this approach, you end up with 2 flavors of the continuum limit, which is sort of what we'd like for QCD, because a lot of processes in QCD only the up and down quarks are relevant. So having 2 flavors is for the one of the physically more interesting scenarios to explore. And so this Hamiltonian was first explored back in the 1970s using strong coupling expansions, and there it's shown that possesses the symmetries that it expect, where translation symmetry, chiral symmetry, which is spontaneously broken, just like in actual QCD. And you have isospin symmetry, which would be present when you have two quarks present with the same mass. You can also show that you recover the SU4 Wigner spin flavor symmetry, which we've observed in nuclear physics. And so this Hamiltonian is a little difficult to map onto a quantum computer. And so the largest calculation that's been done for this 3+1D Hamiltonian lattice is for the lattice shown right there. You have 7 points. And so this is a little too small to learn anything about the physics QCD from. But it can help us understand better what are the challenges involved in mapping Lattice QCD onto quantum computers. So with this that's been done already, we can make a rough estimate of how big of a quantum computer we would need to study realistic continuum physics. As an example, I'll just consider the case of scattering blue balls. So blue balls are just a bound state of gluons, which have been experimentally observed for the first time. So put them onto the lattice for calculations that involve computing blue ball mass. You need a lattice size of 24 by 24 by 24. And to begin to get the continuum limit out, you need to take G around 0.8. Just a rough estimate where the continuum limit needs to occur. And so from this estimate of G, you can estimate the size of local Hilbert space you need on each link. And so using that estimate and the size of the lattice you would need, expect to need around order 10 to the 5 qubits to represent the state of the system. I mean, 10 to the 5 logical qubits, not physical qubits. There's no discussion of doing error correction here whatsoever. And then that's only one part of the problem, because you also need to know how big the circuit will we need to run to actually get physics out. So roughly, you can expect the number of time steps we'll need to do to be around the lattice length. So using some previously developed instructions for the time evolution operator, we can estimate that we need order 10 to the 15 gates to do our full simulation. So these are not small numbers. There's no quantum computer big enough for gates with high enough fidelity to do this that exists right now. We expect in the future, as computers grow, as we do error correction, we expect this to become possible. What do we do in the meantime? So currently, computers we have are too small and noisy to do full 3+1D Lattice QCD. So we can look at simpler models such as QCD and lower spatial dimensions, or with the gluons present, or with report flavors present, to study what simulations on noisy hardware will look like, and use these noisy simulations to develop techniques that will be helpful for simulations. We expect that focus on models that are qualitatively similar to QCD. These techniques will carry over to when we finally do a 3+1D simulation. Particularly, we expect techniques to do state preparation and methods to construct those sort of physical observables we're interested in. Will be carry over directly to the whole 3+1D problem. And it's not just going to be 20 miles long, right? Because there is interesting non-trivial physics that study in lower dimensions, such as jet fragmentation or hadronization, where the way they're currently modeled, they're already effectively treated as a 1D problem. So do a 1D simulation, we hopefully do some simulations that are relevant to our understanding of processes that aren't just a system. So I'm going to talk about one of the projects we worked on to step towards preparing vacuum states for QCD. So we looked at this electrodynamics plus one dimension. So this theory, you have electrons and photons present. And so 1+1D QED is kind of weird, and that is qualitatively more similar to QCD in 3 dimensions than it is to QED in 3+1 dimensions. because in 1 + 1D, the Coulomb potential is linear. So that makes the electric force finite. And so as defined gauge theory, we expect qualitatively similar to speed. So the first thing we looked at doing was preparing the vacuum state. Hamiltonian for a Schwinger model, this QED in one spatial dimension. So from here, we're first we have a hopping term for our electrons with Bell transport review, which describes the photon field, mass term for the electrons, and electric energy. So magnetic energy term because in 1 + 1D there is no magnetic field. So unique quirk of 1 + 1D is that use Gauss's law to completely remove the electric field operator, just replace it with over charges. So once we do our mapping on qubits, find that our Hamiltonian mass term becomes this alternating poly Z term. This hopping term becomes this sigma plus, sigma minus term on neighboring sites. And our electric energy term is the sum over charges squared operator. Charges are just given by a combination of poly Z and identity operator. This maps quite nicely onto qubits. So to compare the ground state, we looked at doing a form of VQE. Like VQE is a hybrid algorithm where on a quantum side compares some state psi of theta, where theta are parameters, some circuits, and you measure the energy, possibly gradient with respect to theta as well. You feed that into a classical optimization algorithm to update theta, so iterate until you have convergence. Previously been applied to many studies of the Schwinger model, SU2 hadrons, there's been some work looking at for SU3 as well. But the challenge with VQE is that you need to figure out some appropriate onsite circuits and optimization algorithm that you can use at scale. So the way I'm doing that was with modification of ADAPT-VQE. So ADAPT-VQE is a algorithm for modification of VQE where you iteratively build up your circuit onsets based on what operators should minimize the energy best by just taking an expectation of H with the commutators of different operators and adding one that has the largest commutator to your onset circuit. So the way we constructed our operator pool for O's that how to choose from, we pick those that should be respecting the symmetries of the Hamiltonian, such as translation invariance and collection symmetry. And then this operator pool, we perform get VQE on several different lattice sizes. So start with 2 sites, 4, 6, 8, and so on, up until we can go any further. And then you get your circuit parameters as a function of your lattice size. And so provided that your lattice that you're optimizing on is larger than a few correlation system, exponentially fast convergence in theta. And then once you have this, these thetas at different L's, you can fit it to function to extrapolate out to larger lattice sizes. And so we looked at doing this for Schwinger model. Oh, sorry, before I talk about that, first I just want to talk about some of the things we need to consider when running on existing quantum computers. So all quantum computers that exist today are noisy, and to get anything reasonable out, there has to be some form of error correction or mitigation done. So generally speaking, there's 2 sorts of noise that exist on quantum computers. There can be coherent noise, which comes from things like relaxation and dephasing, and coherent noise, which can be generated by things like unitary rotations that come from miscalibration or cross-talk events. So there's a lot of ideas on how to mitigate coherent noise, but not so much with coherent noise. This is a problem because we use a technique called polytwirling to convert coherent noise into incoherent noise. And so the idea with polytwirling is for each 2-qubit gate in your circuit, you just conjugate it with poly operators such that in the absence of noise, this conjugated gate would be the same as long as no polys present. You randomly select the polys and average overall basically randomize coherent noise in your simulation averages out to coherent noise, which then you can apply error mitigation to. And so with that in mind, we ran our ADAPT-VQE system sizes up to 28 qubits, where optimization and simulant is done purely classically. And through the circuits we got onto IBM's quantum computer. So here we're just showing expectation of this operator. And so the black dashed line is what came out tensor network simulation of our circuit. And the points are what came off of IBM. And this doesn't look great. These are raw data points where no error mitigation has been performed at all. Once you are polytwirling, it at least looks translation invariant, but it's still completely off. That's because we haven't really done anything to mitigate noise. You just converted one type of noise into another. So there's the technique we use to mitigate errors is known as operator decoherence or normalization. So we know that the remaining circuits in our simulation are all incoherent. And so under the assumption that the noise comes from a poly channel, we know that our measured observable will be directly proportional to noiseless from some unknown parameter, eta. So we can determine what eta is by running the same circuit, just saying the single qubit rotation angle is 0, because you know what the result that should be in the absence of noise. So we can just run that circuit on the computer to see what eta is, and then that value of eta to correct the error simulation. So when we do that for the simulation I showed on previous slides, it takes these four points are all off the curve to pretty close to what we'd expect from the classical simulation. I should mention that this has also been used in a number of other works, and it was first developed here at LBL, work done by Christian Bauer and Bert de Jong. So, like I said earlier, in our optimization on circuit side, qubits up to 28, but extrapolating to larger sizes. And so, using IBM Cusco, we ran on 100 qubits doing the same thing. We show that you still get a good approximation of ground state. So this black dashed line is what comes out of tensor network simulation of the circuit, which is agreement with DMRG calculation. And the points shown are from IBM Cusco, and there's some oscillations around where it should be, but on average, simulation is reproducing expectations back. And I'm not going to show them here, but we also tested this out for other system sizes and found consistent agreement with the average value of chi. It's just this observable average over all the sites. And we also looked at 2-point function for the charges, and that once again, the quantum hardware had good agreement up to a couple of sites separation, but beyond that, your sum of statistics limited. Remember that this is a long plot, so this large error bar actually is quite small. And so here we're able to get the vacuum state, but in general, we're studying dynamics, and so you don't want just the vacuum state. You want to be able to put excitations on stuff on top of it. For example, comparing multiple hadrons and smashing them into each other. We do it now in the state. do that, then we prepare hadron state. So previous studies on how to do quantum simulation of scalar field theories proposed adiabatic switching method using forward and backwards evolution to prepare a wave packet, forward backward evolution, so a wave packet will not move while you're preparing it. And so we can get the same idea to simulations for lattice gauge theories, except we have to be a little bit more careful about how we stop the wave packet because the Schwinger model and other gauge theories, the term that we use, especially on adiabatic, is the term that couples the different sites together. And so the same sort of forward and backwards evolution that works for scalar field theory does not translate nicely over to lattice gauge theories. We tried to make forward and backward evolution work, but we were not really successful. So the alternative we looked at to keep the wave packet from spreading out while mathematics. So first, turn on the hopping term between all the sites in the lattice, except we decouple the region where we're going to put down the wave packet. And then after the state's prepared, we do a second round of adiabatics where we then couple the region with wave packet to the rest of the lattice. And so this gives you a single particle state to prepare one region initial state of hadron. And so here we're just showing that levels as a function of adiabatics, showing that end of the day when you look at the eigenvalues that you can overlap with, they're all eigenvalues energy less than 2 times the mass of the hadron, indicating that this is pretty likely to be a single hadron state. And so this gives you a way of preparing a hadron state. Some simulation, whether it's quantum or classical, but using ideas we use for the vacuum state, not actually necessary to use large these adiabatics on a large lattice, or even do adiabatics on a computer. You can use the same sort of variational techniques on small classical simulations of small lattices and extrapolate to get the circuit. The idea is you prepare a hadron state on lattice, say size 8, 10, 12, so on, just going larger and larger, optimizing a circuit for that specific state and extrapolating the parameters of that circuit to a larger lattice. And so that's what we did. With that state we got, we then formed time evolution. So from a computer, the way you form time evolution is by tritorization. Take your Hamiltonian where not all terms necessarily mute, break it up into individual pieces that you can let independently. And so there's slight complication with this Hamiltonian from the electric energy term. So if you recall back slides ago, the electric energy term has sum over charges on the lattice squared. So we'll have couplings between all sites on the lattice. So naively, you would think that you would need circuits that qubits on every single site to talk to each other. However, we know that for low energy states, these charge-charge interactions are exponentially suppressed due to the presence of confinement. So in our simulation, we can just drop these charge-charge operators beyond a certain distance, and the cost of an error that's going to be exponentially small distance we cut off that. And so this gives us a way of constructing a bit more local circuit to do our time evolution. So another way to do the time evolution, we can track the evolution of hadrons by measuring that same operator chi that we looked at before. This shows the general shape of the circuit we would have. So this first block is just our vacuum preparation circuit that we got before, and then this local circuit puts in a single wave packet. And here we just have our tritorized time. And so the nice thing about setting up your wave packets this way is that if you want to have more than one part present, just take this wave packet block, just copy it over to other parts of your lattice with multiple particles. And so using IBM's quantum computer, we looked at just studying the evolution of a single hadron star with. So that figure down here. So the way to read this, left side is tensor network simulation. The right side is what came off of IBM's quantum computer when we did error mitigation. And the x-axis are just the different qubits, and then the y-axis is time. So in the absence of errors, this figure would be completely symmetric. But computers aren't perfect, so you can see that there's some other stuff happening. But we're able to still track the location of the wave packet out to around 14 or so times x. And so this circuit to go out to 14 times x is actually quite deep. So in this calculation, these 14 steps required a CNOT depth of around 370, using around almost 14,000 CNOT gates. This is, if you use around 10 to the 7 shots, you can actually, there's still a signal that error mitigation can get out. And so even at circuit depths around 370, we're still able to see where the wave packet is at, which was pretty surprising to us because IBM made a pretty big deal of their 100 by 100 challenge. And this is a factor of 4 deeper than that. But even at these circuit depths, we get some physics out. Very pleasant surprise. So, of course, it's natural to compare how long the quantum computation took to classical simulation. So for each time step that I showed in the previous figure, each one took around 30 minutes to process, including both generate the circuit and run on the quantum computer. Processing the results afterwards. And so the nice thing about quantum computer is because everything in the quantum simulation is done effectively in parallel. We want to put in multiple hadrons, take the same amount of time to run them. And we put in 1, 2, or 10. So multiple is necessary if you want to do scattering or simulating systems. However, it's not the same for classical computers because put in more hadrons into simulation, the amount of entanglement in your system as the walls will grow faster. So we expect that the classical compute times, like multiple hadrons, will grow exponentially with hadrons. And for reference, using a GPU classical tensor network simulations, we did this calculation altogether took around 30 minutes. So we're already starting to be in a regime where time to do our quantum computation, our time to do our classical simulation are beginning to become comparable. It's not really, I'm not trying to claim any quantum advantage here. This is still, classical simulation is still passive. And so now this is all the one-dimensional simulation. To wrap up with talking about what we need to go to higher spatial dimensions. So I'm not going to try to jump all the way to 3D. I'm going to start with just 2 spatial dimensions first and consider not having force present. So simulating the gauge fields in 2+1D is a bit more complicated than in 1D because in 2+1D we have magnetic field operators aren't present in spatial dimension. And so these correspond to head operators on our lattice. And so the way these can be implemented in your time evolution operator is by these sort of controlled rotations where controls coming from all of the neighboring links of your head, and you just rotate all of the qubits that are on the head. break it up into just a series of control time motion operators like this. So this looks not too bad until you start counting the number of gates you need. So you truncate the size of the Hilbert space on each link to lambda squared. Squared because you have two integers you have on track per link. You find that the gate count you need scales as lambda to the 16. So this isn't exponentially bad, but it's not practical either. So we would like to find others to reduce this unpleasant gate count estimate. So the idea I worked on with Christian was to look at using a large N expansion where take our SU3 gauge fields, replace it with SUN, take the limit where N goes to infinity, and expand it 1 over our Hamiltonian powers of 1 over N. So this limit's been explored previously in a number of works, and we know it's known pretty well to reproduce many aspects of QCD qualitatively, such as alignment. That's also used in some simulations of hadronization at LHC and other. So what we found for using it on the Hamiltonian of SUC, large N, your Hilbert space simplifies to where you only need to represent what you can think of as loops running around squares in your lattice. So instead of associating the gauge field degrees qubits, which every single link in your lattice, you can assign some to square in your lattice. So this also mathematics simplifications enabled us to perform simulation of 8x8 lattice using IBM Torino again. We show results here where we did started off in a state with no electric fields present, and then just looked at evolution of electric fields as a function of time, and then executed the time steps of operators. So we just stretch out to further times. And compare this to tensor network simulation, but because this is a two-dimensional simulation, MPS tensor network methods are not that efficient, so we were only able to get results out for 2 Trotter steps, which only gets you out to this. But with classical simulations, we were able to perform. We found that we did have good agreement between what came off of the quantum computer and the classical simulation. Also emphasize again that I don't want to make any sort of advantage claim here. You used some form of tree tensor network. Perhaps you probably could simulate stock here as well. We did not explore that because we were focused on just setting up the quantum simulation of this model. And so for this 8x8 simulation, I'm showing here, got out to CNOT depth of 113, which is still not bad. Not as deep as the last survey I showed you, but still respectively big. Wrap up of our near-term goals. So we have a way of setting up hadrons on the computer. So in the future, we'd like to just look at preparing multiple hadrons on top of that, pair them off each other, and begin doing sort of like toy simulations of what we'd like to eventually do at scale, where we're extracting scattering observables directly from simulations. And along the way, we need to determine what are exactly we need to measure to extract this physics. So essentially, I think this is how do we make a detector on our lattice that we measure this operator, it tells us whether or not there's a particle there. What particle there is. And so, so far, these methods of preparing vacuum states and hadron states have only been done in 1D, but we have a way of setting up two-dimensional simulations. So take these techniques, extend them to 2D and maybe 3D as well. And finally, in the margin formalism that Christian and I worked out, we only did that for the gauge fields, but he has forks as well. So we need to include those in the margin limit, which would allow us to do full simulation of 2 + 1 QCD, where you have both your gauge fields and forks present. So that is all I got. Oh, I'm sorry, that's a back slide.
Thank you very much. We do have some time for questions, so anyone in the room, and if you're online, feel free to unmute yourselves and ask questions directly or put them in chat. Questions?
Thank you for the talk. It was really good. I have some questions related to some of the resource estimates that you were talking about. So I think earlier in your talk, you were studying, say, 10 to the 5 qubits, 10 to 15 gates for meaningful simulations. That is what you need, I guess, for something scientifically interesting or something beyond what a classical computer can do. Is that sort of what you're trying to hear?
Yeah, so pretty much anything involving doing real-time dynamics in QCD is beyond classical when you're probing the continuum limit.
So this is for this 24 by 24, right?
Yeah, so this would be something that would be beyond a classical computer.
Okay, but less than that would be something in the regime of classically stable.
Okay, there's probably smaller problems that could simulate classically, or that you couldn't do classically. I just picked this one as an example because I had some numbers that I can confident in.
Okay.
Definitely pretty confident we can't do it on a smaller lattice than this because this is needed just for gases. That we have a pretty good idea of how many qubits we need once we fix our coupling.
Yeah, I see. I was just curious because the classical simulations you were running before already were taking, say, like 30 minutes.
Those were one-dimensional simulations.
Much more reduced systems, right? So it already seems like taking a decent amount of time, right? If this is a much larger scale problem, then I imagine the classical simulation already starts picking up quite a bit. I think even before you get the system to this side, it seems like hard to get. It'd be hard to simulate, possibly.
We'll probably hit the point where things are hard for this.
I think we're at, he said very clearly, right, we're not claiming, but we got to a point where we would need to invest more thought and more resources to get the class. I mean, we didn't present the classical result essentially because it wasn't trivial or easy or however you want to say it. It doesn't mean you can't do it, but I think we're getting to the point where it starts to be hard. Classical. So I think we're at that point somewhere.
I guess also another way I think about this resource estimate is this is an estimate for a problem that people who don't care about lattice, who don't care about quantum, but care about particle physics would be interested in knowing the answer to.
I just had a clarifying point on the classical estimate or the classical resource use. What classical system are you using? Is this like a large scale cluster or is this
Or the classical simulations here? This was using one of the GPU nodes on Perlmutter with QQuantum installed. I think it should be pretty efficient.
So I was also curious about your estimates for number of shots you needed for statistical accuracy. I know this was related in part to the error mitigation, which sort of increases the error bars.
So like where we did 10⁷.
Yeah, and so I mean, that is also a significant factor in the total time it takes to run all of this. Does that also increase as the size of the system increases?
So from what we've seen, no. So at least if you fix your circuit depth, you just increase the system size. The fidelity does not go down, at least for local observables.
I guess that would make sense, but the depth is that is I guess corresponds to the error rates involved. Then you would need more accuracy, or more statistical accuracy. So just shots. So when we're trying to run these 10 to 15 depth circuits, will we need really large numbers?
Probably need error correction where we correct the errors as they occur in the simulation. So you hopefully don't need this number of shots once you have error corrections. It's pretty much, you didn't have to do error mitigation. You could probably get away with like around 1,000 shots or so for what we did here. It's just that the mitigation technique we used for it to work, you need a very large number of shots to resolve a signal. Since if you look at the non-mitigated results here, you don't see a headroom, you just see flat line. Look at it by eye.
Mostly the error mitigation that adds to resource.
The error mitigation is where all that shot use came from. If you have error correction, you should not need to do that. At least not need to do that to the same extent.
Well, once you measure an observable, you'll still have shot noise no matter what, right? But you're saying that doesn't necessarily grow.
I'm curious about you think you have long range terms in Hamiltonian, right? You don't shorter step, but then you're dropping them because correlations increase at the distance. Is this due to initial? But this is real-time dynamics, right? It's not the ground state with some specific properties of the ground state, right? So how do you get the correlations dropping? It's just initial case, initial state that gives you the property, or like how do you?
So that's just a generic property of all the low-lying states for confining gauge theories.
You're doing real time. You're doing real-time dynamics, but you're always
not populating any of the high energy states. So we're just staying in what is relatively low energy subspace of the Hamiltonian for the entire dynamics, where we have this exponential suppression present.
And then in practice, you just drop them from your shoulders.
I guess also in principle, you could just systematically include more and more and just extrapolate.
Any questions online? Well, let's thank the speaker one last time.